As a production or post-production professional, you're constantly bombarded with acronyms, shorthand, and literally an alphabet soup of technical terms.
So in this video, we want to briefly cover some essential terms and vocabulary that we're going to use throughout this title.
Right, so let's go ahead and dive in. First up is, what do we mean by HDR and what's SDR? Well, HDR stands for high dynamic range, and SDR stands for standard dynamic range. And there's a really important thing you need to know. There's a difference between HDR video and what you might know as HDRI, or HDR imaging, which is actually merging multiple exposures together. And HDR video is also different than other multiple exposure HDR approaches, like Red's HDRX. HDR video is a single exposure. And because of that, HDR is all about dynamic range. That is, the difference between the darkest and brightest portions of a shot. Now, for years, we've shot with cameras that are capable of incredible dynamic range, 12, 13, 14, 15 stops of information. But we've forced that information down a small pipe. It's known as SDR, and that's 6 to 8 stops. HDR changes all of that. It maximizes viewable dynamic range, but it does require an HDR monitor.
It's easy to think of HDR as just high peak luminance, high brightness. That's an important component, but it is more than that. HDR is not just brighter pixels, it's actually better pixels. 10-bit or 12-bit color depth, allowing for deeper, more detailed shadows and highlights. And more color, expanded gamuts like P3 and Rec 2020. Now, HDR is often also paired with higher resolution, like UHD or 4K, and can also be paired with higher temporal resolution, frame rates like 48 frames per second or above. Now, it's important to know that these things are not mutually exclusive. You could have HD HDR, or 4K non-HDR, or HDR in any variety of frame rates.
Now, one term heard a lot in HDR is nits. Nits is the vernacular for candelas per meter squared. What's that? Well, it's a measurement of brightness off an emissive surface like a monitor. And nits are often quoted for the peak luminance of monitors or the peak mastering level that you'll use in a project. SDR reference monitoring, for example, has a peak of 100 nits. HDR reference monitoring, and specifically Dolby Vision mastering monitors, have peak levels of 1,000 nits or greater.
So what is PQ, and how was it developed? Dolby looked at real-world brightness, TV and cinema, and envisioned more. How do we mimic closer what we see in the world with brighter, higher color volume? Dolby Labs created a prototype HDR display and had test subjects come in and dial in their preferred white point and black point. This setup was capable of luminance values from 0.004 nits all the way up to 20,000 nits. And 84% of test subjects chose 0.01 nits for black and 10,000 nits for white. These tests, along with other research, became the basis of the PQ, or perceptual quantizer curve, which is also known as an EOTF, an electro-optical transfer function. Unlike traditional video nonlinear gamma curves that were based on CRT physics, PQ is logarithmic and based on human vision. PQ forms the basis for Dolby Vision and other HDR standards like HDR10, and was standardized by SMPTE as ST2084.
Now, the cool thing about the PQ EOTF is that for the first time, the image signal is directly tied to the display's actual light output. This means that when properly set up, a monitor displaying a PQ image will show the specific amount of light output corresponding to the data in the image. And that signal can range from 0 all the way up to 10,000 nits. Also, when properly set up, signal levels on your scopes directly correspond to the display's actual output.
When Dolby Vision is discussed, you often hear the terms Dolby metadata and trims. What do these mean? Dolby Vision uses shot-by-shot metadata, so creatives can make decisions about downstream or lower nit HDR versions and the SDR version of a project's look, and how well they match the highest nit HDR grade. This metadata is described by Dolby in levels. Level 1, or L1 metadata, is Dolby's automatic shot analysis, which generates the base level of metadata needed for Dolby Vision based on the image's content. This also automatically generates a 100 nit target version. L2 metadata is created by what's known as a trim. Trims allow for tonality and color adjustments of downstream versions, meaning the lower nit HDR versions and the required SDR version. Dolby Vision supports multiple concurrent trims. You can have 100 nit, 600 nit, 1000 nit, as many different trim levels as you want. L3 is an optional offset to that level 1 automatic analysis. L5 contains information about the image aspect ratios. Now, in Dolby Vision 4.0, the trim metadata is actually stored as L8 metadata, and L2 metadata is generated automatically for backwards compatibility. Finally, L9 contains information about the source content's color primaries. For the purposes of grading in Dolby Vision, we'll mostly be discussing the automatically generated L1 metadata and the colorist-created L2 and L8 metadata, which dictates the creative intent of the grade.
Another phrase that you'll often hear is tone mapping. What is that? Well, tone mapping is a process where you take a shot's contrast range, gamut, and color saturation from one output medium and map that to the available contrast range, gamut, and color saturation in another medium. This is needed because TVs and video monitors have a wide variety of color volume capability. Each TV, tablet, and phone or video monitor is like a different medium for your content. And Dolby solves this problem with Dolby Vision using a sophisticated method to map both image contrast and color to different types of displays, ensuring that artistic intent is maintained on all devices. The Dolby algorithm actually scales the dynamic range of an image, both in brightness and color, to match the capabilities of the display showing it. Because PQ represents real-world light values and different monitors have different capabilities, you can't just display a PQ image the same way on every monitor. For example, if you graded at 4000 nits and then simply displayed that PQ content on a monitor that has a peak brightness of only 700 nits, the shots will look very wrong. Highlights will be clipped, image detail will be lost, and the creative intent of the grade won't translate. Instead, a Dolby Vision TV knows what it's capable of displaying, and in real time remaps the master HDR grade into the dynamic range that the monitor is actually capable of. Metadata generated during the Dolby Vision grading process guides how this tone mapping is done. And the Dolby algorithms do a great job in this automated process, but they also allow for targeted trim passes, which give the colorist artistic control over the final look. In other words, the tone mapping doesn't have to be just an automatic conversion. And even if the colorist chooses not to adjust the initial automatically generated L1 metadata, because that metadata was made by analyzing each individual shot, Dolby Vision tone mapping can handle a wide range of situations, from very dark to very bright scenes.
Now, as colorists, this is really exciting because it's the closest the industry has ever come to the viewer actually seeing an accurate representation of what the show looked like in the color grading suite. So now that we've covered the essential terms surrounding HDR and Dolby Vision, up next, let's explore the hardware and software requirements for grading in Dolby Vision.